Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hopefully you guys are doing well, had a good weekend, ready to get back into it. Still some people trickling in here. Let me let them in. So let's actually jump in very early. Let's get this right. Okay. So wanted to make sure I can see the chat here. All right, so just wanted to start with some PSAs, some public service announcements, making sure that we're all on the same page, keeping our eyes on the mission, and we're all kind of know what's going on, just to make sure we're all aware of everything. So the last day to withdraw from the class is this Friday, November 6th. Not encouraging anyone to withdraw. I think overall the class is doing very well. As a class average, a lot of you might want to do better than you're currently doing, and that's fine, and you should always want to improve. But just as something you should know, that is the deadline. So, I mean, after that point, there is no return. We're in it for the long haul, and we'll have to want to finish strong. Anyone who's currently on the fence, that is a deadline you should be aware of, though. So I thought I would just mention it. Okay, so in terms of schedule for our class and what we have to keep in mind, by the end of today, you should watch up to lecture 28. And hopefully you're almost there, or maybe you even finished it already, and you can ask me questions about that because you have a quiz next week on everything up to lecture 28. So next week on November 11th, we have our next and last quiz. Yeah, last one. Quiz number 5 next week. And that's going to be the last quiz for the semester. Now, so that's next week. That's 1 week from today. Test 2 will be 3 weeks after that point. So it's going to be after Thanksgiving break on December 2nd. Okay, so next week we have our last quiz, quiz 5. Test 2 is 3 weeks after that point. It'll be after Thanksgiving break on December 2nd. Okay. Our final is Wednesday, December 16th at 9:30 a.m. Now, I wrote tentatively here, but you should definitely think of that as more official because I didn't make that date up. It is actually on the Fordham website. In fact, I do encourage you to go and look up Fordham final exams schedule. You can actually just Google that and it'll send you to the page where you can actually look up the finals and you can know when all your finals are. Normally we know this before the beginning of the semester and I would have put it in the syllabus, but obviously this year has been so crazy, everything is a little bit delayed. So I'm not sure when the final schedule was posted, but I have emailed you guys about it before. I don't remember when, but it's probably about 2 weeks ago, maybe even a little more. Yeah, time is just so weird now in 2020. On one hand, it's like things are going by so fast. And on the other hand, it's like we've already lived 3 years in this 1 year. But I believe it was like a couple weeks ago. So I didn't make up that date. It said tentative on the website, but I think it's more or less going to be official. Every time they put a final exam schedule up and they say tentative, it ends up really being the final exam schedule. So our final will be December 16th. So that is 2 weeks after test 2. And so you have a quiz next week. 3 weeks after that, you have a test. 2 weeks after that, you have the final. The final is cumulative, as I've mentioned before, but just want to remind you. So if you didn't do well on test 1 or on some of the quizzes, the final is going to be your opportunity to show that you've now learned and you've improved and you now understand things a lot better than you used to. And if you can finish strong, that is good. I definitely consider improvement as when I'm assigning grades. So I understand not everyone learns at the same pace, and some people just might take a while to get in the groove. And so they might not start out strong, but if I see steady improvement over time and I realize you're ending strong, then that means a lot to me and it's worth rewarding as far as I'm concerned. Okay, so that is just the general schedule. So it's going to be over in about 6-ish weeks is when it's going to happen. So after 1 week, quiz 5. After 3 weeks after that is test 2. Then after 2 weeks after that is the final. And hopefully by that point, you guys will be in good shape. So that being said, I definitely want us to all finish strong, to keep our eye on the prize. I know it's been a rough time for all of you, but hopefully we can finish strong and all band together. I do want to encourage you guys to participate as much as possible, probably more than you've ever been before. Don't be afraid to ask questions. Don't be afraid to speak up. And I know I'm going to reiterate this. I said it before, but I know in the beginning I said like you guys don't have to have cameras on or anything like that. And that was because, I was concerned about your privacy and I was recording, and I didn't realize until recently that I could actually spotlight it so only my video gets recorded and none of your videos get recorded. So just to feel like we're all here, we're all in this together, you're not alone, I would encourage you to use your cameras if it's possible and you're comfortable enough. Highly recommend it, just so you can see that there are other people out there, and we're all in this together. And please speak up, please interact, please reach out to me when you have issues, all that good stuff. In fact, over the last few weeks, after I've given all my classes tests and quizzes at this point, and of course, after the first test, I talked with a lot of students who felt they could have done better, and I was talking to them and giving them advice and how to improve, and the issues that they raise are not new, and sometimes you just have to reach out and talk to someone. Sometimes you're sitting there by yourself at home, things aren't going so well, and you just feel like it's impossible because you feel like you're by yourself. But if you were to reach out to someone and say, hey, I'm having these issues, I'm having these concerns, how do I fix them? Reach out to me, reach out to a tutor, reach out to an advisor, reach out to somebody. Hopefully you're comfortable enough to reach out to me, and I can help you, and we can help you figure out the way to actually improve and get better. So I'm actually thinking, because during these office hours, there are a lot of things that have consistently come up that I'm realizing that are obvious, but not so obvious. Like, I mean, in general, when it comes to doing well in a math class or any class, the steps you have to take they're obvious as conceptual ideas. Okay, I have to do my homework, I have to study, I have to spend some time on this. But in application, when students actually try to apply these principles, I find a lot of them just don't do it properly. And so they end up spinning their wheels. They end up, again, getting frustrated because they are doing the work, they're putting in the time, but they're not getting the results they want. And so now it's like, what's wrong? And when they're not aware that they're not doing things as efficiently as they could be, it now comes down to, well, what's to blame for my performance? And of course, as the teacher, I get it. I get a lot of that blame because I'm the guy who gave you the grade that you don't like, so I get it. But at the same time, a lot of times it's just that students aren't applying the things that they do know how to do very well. And so I've been thinking about maybe having like just a general, I want to say like a study hall or something like that, maybe like a talk or mini seminar or something. Probably on Friday, I think would be the only day I would be able to do this. So I haven't come up with a schedule yet or anything, but I'll probably, just to throw the idea out there so you guys know what I'm thinking, and maybe I'll send out a doodle poll or something to try to get a schedule together. But just just a meeting outside of regular class time where I can just talk to you guys about improving, about how to study, some of the things that you could do better, some of the things that you're doing okay with, just to talk about some of the nuances, which I think a lot of you would benefit from. So that's just something I would probably throw out there, and I'll probably email you guys about that at some point, just to make sure that we're all finishing strong. I'd want this, of course, to be some point soon, maybe within the next week, so that you have the next 4 or 5 weeks to actually implement a lot of the advice that I would talk about. Okay, so those are just some things that I want you guys to be aware of in terms of schedule, in terms of, you know, keep your eye on the prize. It's been a crazy year. It's been a crazy semester. I do get it. And hopefully you guys can finish strong, and we can all finish strong, and we can end this this semester and this year on a strong note. Okay, so that being said, that was in terms of schedule. Now, what I do want to mention is just a little bit more specifics on the actual quiz that you will be doing next week. Same deal, really, in terms of how it's going to be administered. It's going to be on Gradescope. You're going to log into Gradescope at 8:30. You're going to take the quiz. Okay. After that, we'll go through the quiz. Maybe if not that same day, if you guys don't want, we can go through it the following week, because we have some time, right? So after that quiz, I can probably give you guys a day off, so we can meet up the next time and go through the quiz. But yeah. So at this point, I want to kind of ease up on the amount of work I'm giving you in terms of quizzes and tests, and just kind of get you guys to start focusing, give you guys time to go back over test 1 material. Make sure you don't forget it. Make sure that if you weren't good, you have time to keep up with the class and also go back, because the final is going to be, as I said, cumulative. So even past topics are going to be important for the final. Test 2 is not cumulative. Okay. So yeah, so that's the plan. So in terms of the quiz, specifically quiz 5 that you'll have to do next week, there are really 4 main topics, as you can see here. One of them I actually tested you on before, but that's because I spent 2 lectures on this topic, and your last quiz ended after the first lecture, so I could test you on that. But then after that, I continued to talk about that topic, and that was related rates. So related rates, I will test you on that again. So you get another opportunity to show that you've learned about related rates. Related rates and optimization, remember, these are 2 word problem types. So a situation is going to be described to you that you have to translate into mathematics and actually solve the problem. So related rates, definitely something you'll need to know on the quiz. You know, you're looking at a related rates, well, I'll probably talk about that in a little bit, or just based on questions that I get later. Another thing that you need to know for the quiz next week, which I believe I tested you in a bonus on the last quiz, is absolute extrema. I think extrema in general, actually. Maybe I would also put that. Let me try to absolute and local extrema. Okay. So extreme points, remember, that's just a fancy name for maximum and minimum points, the highest value, either in a local sense or a global sense. That's the difference between absolute and local. So local just means you're the maximum or minimum within some small region, versus absolute. Maximum or minimum means you're the maximum or minimum on when you're looking at the entire global scale. So that's also called the global extrema, or global maximum or minimum. Local extrema, also called relative maximums and minimums. I expect you to know about both of these. I also expect you to know about critical points. What are they? Why are they useful? How do you find them? So all of that is going to be important for the quiz as well as curve sketching and graph features. So we went over a lot of features in class. So not only is sketching curves important, but you need to be able to identify things like the domain of a curve, the asymptotes of a curve, the intercepts on a curve. What are the x-intercepts? What are the y-intercepts? You have to be able to know, when is the curve increasing? When is it decreasing? When is it concave up? When is it concave down? When is there a maximum? When is there a minimum? When is there an inflection point? So when I say graph features, those are the kinds of things that I'm talking about. You should know what they are, how to actually find them, how to compute them. Now, for the quiz itself, I'm not going to actually ask you to sketch anything. I will ask you to do that on a test, but on the quiz itself, I won't ask you to do that. But you would have to know how to sketch something, because I might have to I'll ask you to identify graphs, maybe match equations to graphs, maybe talk about, give you a graph and ask you about features of that graph. So you do need to really know this stuff, even though you're not going to actually physically need to sketch a graph for the quiz. You will need to know how to do it for the test, and knowing how to do it will actually help you answer the quiz problems anyway. So just by knowing how to do it, you will know how to answer the questions that I'm going to give you. So definitely focus on sketching, even though technically for the quiz, I'm not going to ask you to sketch anything. But I'm definitely going to test your knowledge on graphs and the features of graphs. Then there's optimization. So optimization is another word problem. We also spent a couple lectures on that. Make sure you know about optimization. What is it? How do you recognize an optimization problem? How would you solve an optimization problem? With related rates, well, with related rates, curve sketching, and optimization, I actually gave you guys a strategy, a sequence of steps. There were handouts that are posted on the website, and I believe in the YouTube video description. I want to make sure. But if I didn't post those in the description, you can also see it on the website. So I have handouts for related rates, handouts for curve sketching, handouts for optimization, where I basically give you a summary of, here's how you recognize when you're seeing one of these problems. Here are the steps you take once you realize you're looking at one of these problems, and those should be fine. So these, again, everything here is just applying the things that we've already learned about, applying derivatives and all that stuff, and going over. I have a question here. Is there an answer sheet for the problems on the related rates sheet? No, because I go through a lot of the problems on the sheet itself. So you'll see the answers in class. In terms of the other ones, I often encourage students to actually try them on their own. And if you have questions, then you can reach out to me. You can ask me in here, or in office hours, or something like that. So while I don't have a document where I have all the answers in there, I do go through most of the problems in class, so you'll see the answers there. And for the others, I'd like you guys to try it, and actually, if you're not sure about the answers, or you're getting stuck, I'd rather you reach out to me than actually just read the answers somewhere. Okay, so that's kind of where we are. So now you understand the overall schedule. Hopefully you understand somewhat of the mindset, which I guess if I do have that extra meeting with you guys, I'll talk about that, just like overall mindset, how to make sure that you're actually focused on the end goal and you're not too worried, and how not to lose time and focus because you're worried about the wrong things. But hopefully you're getting into the mindset, you understand the time, you have a schedule, you have deadlines, you need to end strong, and these are the things that you need to cover. So with that being said, I've talked for a while. I would like to, one more thing to say. As you guys always also know, I tend to like to give bonus problems on my quizzes. And so I'll just talk about the topics for the bonus material. So if you go beyond lecture 28 and actually watch more, the topics that I will immediately follow optimization, we move on to another phase of calculus, which is the integral calculus, which I mentioned in the first class, the first couple classes. So you'll start to talk about definite integrals, things like Riemann sums, antiderivatives, and the fundamental theorem of calculus, right? So if you want to go ahead and learn about those things, if you're very comfortable with the 4 topics that I've already mentioned, and you have time to go ahead and maybe watch the videos here, maybe read some stuff from the textbook, practice a few problems. Bonus material would be samples from those topics. So yeah, so that's where you'll have the quiz. So the quiz essentially covers those 4 topics, but if you're very comfortable with those 4 topics, you want a little bit extra icing on the cake, I would go ahead and start to look into definite integrals, Riemann sums. Only do like the finite Riemann sums. We don't do the infinite Riemann sums in this class. So things like knowing how to apply the left-hand rule, the right-hand rule, the midpoint rule with 4 rectangles or something like that. If you didn't cover that topic, you probably don't know what I'm talking about. But if you do cover that topic, you'll now know what I'm talking. You'll know what I'm talking about. So make sure you can actually get through some of those. Okay. So that's where we are, and that's the schedule. And at this point, I would like to open things up to you guys. Q&A, questions, concerns, comments. Please let me know if you have any questions about these classes, about this class, about these topics specifically, but I guess also just some general concerns or things that you want to know, because I only get to meet with you guys once a week. So yeah, at this point, please. Yes, the quizzes were graded from last week. And I actually also went over a quiz. Did I not send those out to you guys?
I didn't get the grade either. I looked on Jupyter and I checked Gradescope, but there was no.
Yeah, so
grade,
maybe I
just said
forgot to send.
submitted.
Maybe I forgot to actually publish the grades and send out the email. So I will definitely work on that. Note to self. Note to self. Publish quiz 4 grades. Okay. So the quizzes are pretty much graded immediately after you take them. So yeah, they're pretty much auto graded because I don't actually check your scrap work for quizzes. So yeah, I may have forgotten. Like I said, it's been a crazy time for everybody. So it's possible that I forgot to actually send out that email. But so I will do that. I will send those out right after class. Sure, we can go over any specific problem you want. So we have a question on related rates already. So we can do that. Maybe I can actually. Actually pull up the document. Give me a second. Problem 6. So there it is. Da, 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 da. Okay, so this is related rates. Let's actually talk about that a little bit. So one, related rates. Maybe just before we do the problem, I am going to get to the problem, but maybe let's just talk about related rates for a little bit. So related rates is a word problem. How do you know it's a related rates? Maybe someone can elaborate like on that? Like I see this word problem. How do I know it's a related rates word problem? Yeah, it mentions something changed at a specific rate. Yes, this is true. So and then what? What are the kinds of questions that you can be asked? So related quantities are described. So they might tell you about the length and the width of a rectangle, or the radius and the diameter of a circle, or they'll describe some situation to you, some physical situation, where they'll tell you about different things and how they're related to each other. And then you're given rates of change for some, and you're asked about the rate of change of another. Okay, so that's how you'd notice, right? So in this question specifically, question 6, which we were asked about here, notice here it talks about the radius of a circle is increasing at a rate of blah, right? What is the rate of change of the area of the circle at the instant the area is this, right? So they're describing the situation to you. There's a circle. They're talking about certain quantities, namely the radius and the area of the circle. You're told about the rate of change of one of these quantities. You're told that the radius is changing at this rate. Then you're asked about how fast something else is changing. How is the rate of change of the area, right? So this is something that you should recognize. Just by reading this word problem, you should know what you should be doing, how you should be approaching this problem. Once you identify it as a related rates problem, which this one now clearly fits the mold, there's a 6-step process. So how to solve, right? So how to identify a related rates problem. So those are the identifying markers. How to solve a related rates problem. So there was a 6-step process. Okay. So one was to read. First, you have to recognize that it is a related rates problem. You have to pick out the specific information. 2, diagram. If possible, necessary. We'll talk about when it's possible and necessary, although I did talk about this in class. 3, write down what you know. And what you want. And when you want it. 4, you come up with an equation. This would be the reason why you would want a diagram. If the equation is given to you, which on rare occasions it would be. You don't actually need the diagram. The diagram is drawn so that you can actually figure out how to set up the equations, right? So if you draw like a box and it asks about surface area, then you can actually count the sides on the box. You can visually see how you would construct the surface area, what areas you have to add. So the diagram is really helping you to come up with the equation. Also make labels for the quantities so that you know how to call them in the equation. Then you're going to differentiate implicitly with respect to time. And then you now solve the problem, right? You plug in knowns, solve for unknowns. Not always, but you may need step 4 to assist you here. So sometimes you'll realize you have too many unknowns at this point, and so you don't have enough things to plug in to solve for the thing you want. So usually when you end up in that situation, the trick is to go back to step 4, use the original equation that describes everything to figure out the quantity that you need to find, and then you come back and you plug these in. But this is the related rates problem, pretty much a 6-step. You should know this as a matter of just memory, right? And after doing enough problems and always writing out the steps, hopefully you'll have these steps kind of memorized, kind of internalized by the time you get to a quiz. The more you have it internalized, I know technically you can look up the paper, you can look up the sheet and go through the steps, but the more you have it internalized, the better for you. And that is something that students just don't get when they are in a situation like this. They just think, well, I can just look up the handout. I don't have to memorize the steps. But it turns out that you are far less efficient if you don't know the steps and you have to look it up and then be going step by step. You lose a lot of time and you'll end up losing a lot of points in a quiz. So I do recommend that you do know these steps. When I'm giving these exams on paper, the students do not have the handout. And so the problems aren't written to the point where you should expect it to be having in the handout. Okay, so that being said, let's actually do this. So this was asked about. So again, what do? 1, we read. So yes, we recognize it's a related rates problem. We actually already read it. 2, diagram. Okay, so it talks about a circle. So okay, here's my circle. That is the radius. And we also mentioned area. So A, let me call A equals area. So the area is just the amount of space this guy takes up. So that's my diagram. That's my R. 3, I want to write down what do I know? What do I want? When do we want it? Now. Okay, so what do we know? I use my diagram. I call my radius R. And I know how the radius is changing. It's increasing at a rate of 1. So I know that dr dt equals 1. Specifically, +1 because it's increasing, right? If the problem mentions decreasing, I know that it should be -1. My handwriting is all over the place there. Okay. And that's the only rate I was told, right? So now I write down what do I want? What is the instantaneous rate of change of the area? So what I want is the rate of change of area. And I write down when I want it. When do you want it? At the instant the area is 4 pi. So this is when A equals 4 pi, right? And so that's going to be the 3rd step. By the way, if I'm confusing you and you need to stop me at any point, okay? Don't be afraid to interrupt me. Now 4, we're going to come up with the equation. The equation should relate all the variables that I've mentioned heretofore. Okay, so there are only 2 variables that were mentioned, A and R, A for area, R for radius. So now I just want an equation that relates the 2. Now me drawing this diagram should sort of conjure up visions of high school geometry, and you should hopefully come up with the equation A equals pi r squared. Okay, so, and this is also mentioned in the handout as well, that I do expect you to know basic geometric formulas for area, perimeter, things of that sort. Not for anything crazy. So just know things for triangles, like right triangles, like Pythagoras' theorem, know about the area of a circle, know about the circumference of a circle, know about the radius of a circle, know about rectangles, all that stuff. So I do mention the kinds of formulas that I would expect you to know. Other than those, I would actually give you the formulas, but at this point, hopefully everyone knows that the area of a circle is pi r squared. So that's the equation. So now, once you have that equation, you're going to differentiate. Now, it's very important that you realize that the differentiation here is implicit with respect to time. A t is your independent variable. So the derivative of a is dA dt, a prime. The derivative of this is 2 pi r dr dt. So remember, you have to multiply by the derivative because of the chain rule. So that's that. Students often forget this, don't forget. Okay. And now that brings us to step 6. So at this point, we're going to want to plug in. Now I know what I want. I want this guy. This is what we want. So now I have to go and plug everything in to find that guy. Okay, so my dA dt is equal to 2 pi r. Well, dr dt, I know this is 1. So this was given. But now you realize r. Was r given? I don't know. So you go here and you're like, where did they tell me about r? Where did they tell me about r? Nowhere they told me about r. So you come at this point and you're like, oh, wow. At this point, I have to plug in, but I don't have all the information. What do? Back to step 4. What happened in step 4? In step 4, we discovered the equation was pi r squared. And we know, or we want, the a to be 4 pi, right? That was written down here. Okay. So now you go in and, okay, so this means I need 4 pi to be equal to pi r squared. This means I can divide both sides by pi. And so that means 4 is equal to r squared. This means your r is equal to 2. Of course, you reject the negative 2 because it's a magnitude. So technically it's plus or minus 2, but you say it's 2 since it's a magnitude. So now you realize r equals 2. And now you go back and you plug it in there. So I go back here. So this means my dA dt is 2 pi times 2 times 1. So dA dt is 4 pi. And the units here, as I mentioned to you guys, I don't particularly care whether you get the units or not, but I'll write them down here. It's that's actually a typo. That shouldn't be cubic. That should be square. Area is square units. So area would be meters squared per minute. But if you get the figure 4 pi, that's good enough. Okay, so the person who asked the question seems that they got it in the chat. Any other questions? But as you can see here, just me knowing this process and following this process, just follow my nose, we could actually get through this problem. So read to make sure I recognize it as a related rates problem so I know what sequence of steps I need to take. Diagram, just to get my bearings so I can see what's going on visually, kind of fix things in my mind, how things relate to each other, how they work. Third thing, write down what I know, what I want in terms of the variables that I use to construct my diagram. 4, come up with an equation that relates all the variables that I use to construct my diagram. The diagram itself is going to be helpful in that. 5, I'm going to differentiate. Remember, we're differentiating with respect to time. So you apply the derivative rules as normal, but you have to multiply by the prime because of the chain rule. So every time you differentiate an r, you multiply by dr dt. Differentiate an a, multiply by dA dt. Differentiate a p, multiply by dp dt. Differentiate a q, multiply by dq dt. If you differentiate anything that is not a t itself, you have to multiply by its derivative. Okay, so that's what implicit differentiation means. Then you go and you plug in. Ever so often, you're not going to have all the information that you want to plug in. At this point, you don't panic. You don't think there's something wrong with the question. You go back to step 4. Once you go back to step 4, you'll usually be able to find the information that you need, and then you can come back and plug it in. And at the end of the day, that should give you the answer. Okay, so that's related rates. Any questions on this? Okay, we'll take that as a no. Let's talk about these guys. Absolute and local extrema, critical points. So here, just using f of x to be a generic differentiable function. Twice differentiable at least. Tell me about critical points. What is a critical point? How do we find them? This is where participation comes in. Zeros of the first derivative, almost. Yes, Maria?
Oh, I was going to say that usually they occur wherever the function, the first derivative and the second derivative are equal to 0. Well, you kind of set it equal to 0, and then you can solve for x, and usually those are critical points that you can use to test for.
Yeah, but just give me the definition of where they come from. So I think you mentioned first and second derivative.
Yes.
How do you use those to come up with the critical points?
Set them equal to 0, figure out where they don't exist.
Right. So just to refine that answer, and I think someone in the chat also got it. So for critical points, you only need the first derivative. The second derivative is useful, but not for identifying critical points. The critical point, these are points where f prime equals 0 or f prime is undefined. Okay, so those are the two things you search for. You're going to look where the derivative does not exist. You're also going to try to find where it's 0. And there are a couple of reasons for this. We know that derivative undefined can be a maximum or a minimum because we know about examples like the absolute value of x, where the derivative does not exist at 0, but it's clearly a minimum. So when the derivative doesn't exist, like at sharp corners or things of that nature, we can have extreme behaviors at these points. So we'd want to identify those points. Also, we have something called Fermat's theorem, which tells you that if the derivative does exist at an extreme point, then the derivative must be 0 there. It does not guarantee that if your derivative is 0, that you would have a max or min there, but it is definitely a point of interest. It's a point that you do want to check whether or not it's a max or min there. And so these guys, we call them critical points because these guys are the 2 points that we'd want to focus on. So when it comes to critical points, the first derivative is going to define where those guys are. Let's, I want to not get too wide. So the first derivative is what you look for. Oh. Hopefully that's the resolution it was on before, is undefined. Right? So, and again, undefined just in terms of continuity. So you know that if it's a fraction, anywhere the denominator is 0, it's undefined, etc. If it's a polynomial, then of course it's defined everywhere, so you only find the zeros, etc. Right? So it's 0 or undefined. Okay, so that will give you critical points, right? We like these critical points because they tell us about where extreme points where extreme points may occur. They will also tell us about where different behaviors will occur. So if I want to know where it's increasing, decreasing, concave up, concave down, the behavior of the function will be the same in all the regions separated by these critical points. So I would just be able to test in between these critical points for increasing, decreasing, concave up, concave down. So that's why they're important. So tell me about finding absolute maxes and minimums. How do we do that?
Like, are you talking about when you test the critical points that you came up with?
Right. So given f of x on an interval a, b, where f is continuous, find the absolute max or absolute min on AB. Every now and then, I will hear students respond to this question by saying something like, well, there is no absolute max or there is no absolute min. However, in this particular situation, we have a theorem called the extreme value theorem, which says they are guaranteed to occur. So you definitely should have an answer here. So if you have a continuous function on a closed interval, it will attain its absolute max and min on that interval. This is the extreme value theorem. How would you find it? So there's a 3-step process to finding it. What was the first step? So you'd find all critical points in AB. And evaluate F there. So that's the first thing. So you find all critical points, you plug them into your function, you get the output value. What is the second thing you need to do? Plug in the endpoints. Find f of A and f of B. Plug in endpoints. Third thing, what's the third thing? Third thing is to compare, right? So here you know that the highest value above is your absolute max, and the lowest value equals absolute min. And you would write as example, f of 1 equals 5 is the absolute max. All right, so I expect you to identify the x value and the y value when you're given the answers here, usually, right? So I'll say at x equals 1, the function attains its absolute maximum, and this absolute maximum value is 5, right? So that was absolute max and min. How do you go about finding local max and min? There are actually tons of ways. I would recommend. Well, there are two main ways. I'm sure you can go about it some other ways as well. But in a Calculus 1 class, there are two main ways. I would recommend, though, the first derivative test. There's also a second derivative test for finding absolute maximums and minimums, but one, it doesn't work in all situations. Your second derivative has to be defined for you to even apply this test. And two, you have to kind of do the first derivative test anyway because of other things I'll be asking you. So I'll ask you about increasing and decreasing as well. And the first derivative test also gives you information about that. So the first derivative test is something you'd be doing anyway, so you might as well squeeze all the information out of it that you can. The second derivative test would be an extra step that you'd have to take, and it's also does not work in every case. And so I would probably recommend that you always do the first derivative test when doing this. So the first derivative test is find and plot critical points on number line plug in values in between these points into f prime, right? You plug into the first derivative because it's the first derivative test. Then you can classify based on pattern. So we saw that, okay, so let's say here x is your critical point and f of x is continuous here. And when you plug in the first derivative on the right side and it's positive, that means it's increasing. If you plug in the first derivative on the left side and it's negative, that means it's decreasing. This would mean this guy here is a maximum. Again, x critical, f continuous if you were to plug in a number to the left side of f, and you found that on this side it was negative, that means decreasing. And if you plug it in on this side and you realize, and this is not the same x, it's some other x that's it, like right to the right or to the left, and on this side it's increasing, that means this is a local minimum. And you can also know about increasing and decreasing right away. So you'll also get the intervals of increasing and decreasing, which is often something that I'd ask you about anyway. So the first derivative test can actually kill two birds with one stone. You can know about where it's increasing, decreasing, where the maximums and minimums are. Yeah, so that's how you would find the local extrema. Find the critical points, which now we know is where the derivative is 0 or undefined. You'll plot these points on a number line, plug in numbers in between those points into the first derivative. When the first derivative is positive, it means you're increasing. When the first derivative is negative, it means you're decreasing. If you're increasing on the left, decreasing on the right, you have to hit a maximum. You have to be the biggest in the middle. If you're decreasing on the left, increasing on the right, you have to be a minimum. You have to be the smallest in the middle. Of course, in order to actually be the maximum or minimum point, you have to exist. So the function needs to be there. So you can't have a hole or a gap or an asymptote or anything like that, a vertical asymptote or anything like that. You'd have to actually be there. So that's where you check continuity, which is why in curve sketching, I often ask you in the beginning to find the domain. So you know all the points where your function would exist. So you'll know whether that critical point is actually on your graph or not. And so that's how you go about finding the local extrema. And that's critical points. And those, again, these guys are the main principle, but the principles themselves kind of tells you what you need to do, right? So find the critical points. Because you know the definition of what a critical point is, you'll be able to find those, plot them on a number line, plug in numbers in between, and you just test them like that. Let's maybe also just cover curve sketching and graph features. So in Calculus 1, whenever I ask you to actually sketch a graph or identify a graph or do stuff with graph or identify certain features, there are a list of features that you're going to want to know how to do. So features useful for sketching. And of course, the features are useful for other reasons. Sketching is something that we test you on in Calc 1 usually, not because in real life you're ever going to have to sketch a graph by hand, but it's a very tangible way for me to test whether you understand the concepts, right? Like if you understand what a maximum is, what it means to be concave up, what it means to be concave down, etc., you being able to draw a picture shows me that you know what that means. So if you draw something and the shape is like a frowny face and you interpret that as concave up, I will know that you actually don't understand the concept of a concave up, right? So it's a very visual way for me to tell that you understand. However, that being said, and I spoke about this in class, these features are actually important when the function is something important to you. A function being concave up and increasing actually means something. It means something is going up and it's going up at a faster and faster rate. And so a lot of times when you want to know about certain things and you sketch those things out, how the graph looks, how it's shaped, the graph features actually will give you information about the thing that you're tracking. And that's the important knowledge that we want you to have. However, it's very hard for me to test you on that in a math class. So curve sketching is a very visual, visceral way that I can actually know, okay, this person understands what concave up means, right? So there are certain features that are important for interpretation purposes on a graph. But I would know that you know how to interpret these things by actually being able to sketch something. So there are features that you'd want to know. So one domain. Now you've been finding domains since forever, since algebra class. So I don't think I have to explain more about finding domain at this point. Two, intercepts. Right, so your x and y intercepts. Again, something that you've been finding forever. I don't think I need to explain that. To find the x-intercept, set y equals 0, solve for x's. To find the y-intercept, solve for set x equals 0, solve for the y's. Three, you'd want to figure out if there are any asymptotes. Now, there are many kinds of asymptotes. In this class, there are two that we care about. There is the horizontal asymptote. And you should remember to figure these out, you would find the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. And if any of these are constant, say k, so you find the limit and it's a constant, and the constant is k, could be 5, could be 3, could be 1, could be whatever, then y equals k is your horizontal asymptote. We also care about vertical asymptotes. And this pretty much this is when you have an infinite limit. So if you approach x equals a, either from the right or the left, and you go up to infinity or negative infinity, that is a vertical asymptote. However, you can identify these pretty quickly in the cases where I am going to ask you about. So we care about polynomials and rational functions. Okay, so a vertical asymptote, this is x equals a such that the limit as x approaches a from the right of f of x is plus or minus infinity, or the limit as x approaches a from the left of f of x is plus or minus infinity. So that is the technical definition. However, I'm only going to ask you about two situations, polynomials and rational functions. And for these, you would know that these guys have no VAs. Also, they have no HAs. And for rational functions, VAs occur where the denominator equals 0. So you can identify the points where one of these behaviors will occur if the denominator is 0 and this cannot get canceled. The 0 factor is not canceled by anything in the numerator. Okay, so if you have like a factor of x minus 1 in the bottom, so you're like, okay, x equals 1 is going to make the denominator 0. But at the same time, you have a factor of x minus 1 in the top, so the x minus 1s would cancel. Then what you get in that situation is a hole. You don't get an asymptote. Okay, so you'd literally have to have an x minus 1 in the bottom, a factor of x minus 1, and there's nothing in the top that cancels it. So there's nothing to get rid, to simplify away that division by 0. Whenever that happens is when you get an asymptote, a vertical asymptote. So you should know about asymptotes. Four, the features that I would ask you to find is where it's increasing, decreasing, I'll ask you intervals about this. Max, local max and mins. And here you would just use the first derivative test. And it will identify all of that for you. The fifth thing I would ask about is intervals of concavity. Where is it concave up? Up like a cup, like a smiley face, and where there are inflection points. Okay. So I would ask about both of those. So how you would do this is you use the concavity test. Very similar to the first derivative test, except you use the second derivative. So concavity test, let's see what that is, just to remind you here. So this is where find where f double prime equals 0 or undefined and plot. Then you can plug in numbers in between. And classify based on the pattern. So what is the pattern? So something like here x, where your second derivative equals 0 or undefined, but f continuous. If you go on the one side and you find that the second derivative is positive, this means concave up, up like a cup. If you go on the other side and you see the second derivative is negative, this is concave down, down like a frown. So this here means concave up, this here means concave down. Now, if we switch concavity, so you switch from concave up to concave down on either side, x is an inflection point. If concavity switches on either side. Okay, so in this case, you'd have an inflection. In this case, you'd have an inflection. So again, here's your x. Second derivative is 0 or undefined. F continuous though. Then you can have your second derivative is negative on this side, which means you're concave down like a frown. Second derivative is positive on this side, concave up like a cup. Then in this case, again, x is an inflection. Of course, in all other cases, no inflection. Okay, so very similar to the first derivative test, except you use the second derivative, and this is called the concavity test. So then you'll be able to tell me where you're concave up, where you're concave down, and you would be able to identify those features on the graph. And hopefully at the end of the day, practice actually sketching that out, being able to draw a graph with all these features, which would be the sixth thing. And we also know what that would entail. You'd start by plotting intercepts. Yeah. Plot intercepts. You would plot max, min inflections if they exist. You'd faintly draw out the intervals of increase, decrease, and intervals of concavity. Right, and I showed you in class how to do this. Way below the graph, you kind of just sketch out where things are behaving, how they should be behaving, and then you draw a curve going through. Passing through all the points you plotted. And of course, it has to obeying all features found in steps 1 to 5, right? So if you found that it was increasing in this region, then make sure that your picture, the graph is going up as you move from left to right, right? So you need to make sure. So if you do calculations and you tell me that the graph is increasing at some point, and yet on your picture that you sketched, the graph is moving down as you go from left to right, I'm going to understand that you don't really know what increasing means, or you're just not paying attention, which neither of those should be true when you're on a test. Okay. Any questions on, again, I've been talking for a while. I want to make sure that there are no questions on anything I said here. There are probably questions if you didn't watch the lectures yet, but at this point, it's probably best that you actually do go through and watch the lectures, because I do examples of when I go through everything here. So the recap I'm doing now is kind of under the assumption that you've already watched the lectures, and I just want to highlight to you what the important things you should have come away with. But if you didn't go through the lecture and you don't practice the problems, none of it's really going to stick. So hopefully, but just as an idea, was there anything I was going over as I was going over it? It like didn't make sense to you? I mean, now would be the time to bring that up. Okay, well, at least Daniel's responding to me. Grateful.
I was also fine with the steps. Didn't
Okay.
have any questions.
Okay, awesome. Thank you. Sometimes I feel like I'm alone here. It's nice to know that there's someone out there listening. Okay, what optimization? I don't know if everyone got to optimization, but thanks. So yeah, and sometimes even if you don't have questions, if I just ask you guys, everything's okay, just check in with me and let me know that, yeah, I don't have any questions, right? Just have that interaction going, right? Just we have that conversation so I can know, am I talking gibberish? Are they understanding me? So let's actually talk about optimization. Optimization is, again, another kind of word problem. It's a little bit more involved than related rates. Not much, but enough. It's significantly different. You have to actually cover more things in an optimization word problem. But it's also 6 steps, at least how I set it out. So how to identify that the word problem I'm reading is an optimization problem? Okay, so again, a situation is going to be described in words. involving some quantities of interest. You'll be given some restrictions, and then you'll be asked to optimize the situation under these restrictions. And for us, optimize means to maximize or minimize. As appropriate. Okay, so you might be they might describe a situation to you where it's like a business scenario and they're like, okay, we want to maximize our profits, right? So however, we only have this many things to work with, right? So they'll describe a situation, hey, we're selling this product, we can only sell this many per day and blah, 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 blah. We'd like to maximize our profit, right? So that's, you're given some restrictions, you want to optimize under those restrictions. Or you're told that, oh, a farmer has 100 feet of fencing, he wants to build a rectangular fence, a rectangular enclosure. How can he build it in such a way that he can plant the most crops? And the interpretation of that is that the length of the fencing is the restriction, and the thing you want to optimize is area. How you want to optimize it? You'd want to maximize the area. If he wants to plant the most number of crops, he would need the biggest area to do this, right? So that's how these problems will be arranged, right? So they're just going to describe some situation to you. There's going to be something that is described that you only have a finite amount of. We always have a finite amount of resources. But within that situation, we want to make things as good as they can possibly be. So we want to maximize profits, minimize cost, maximize area, minimize surface area, things of that sort. Okay, so the way that you're going to make a situation as good as it can be would be to use calculus, right? And to find maximums and minimums. Again, it's going to come down to doing first derivatives and finding maximums and minimums, right? So how to solve? It's also, as I mentioned, a 6-step process. So one, as always, you read, because you'd have to realize that it's an optimization problem and you'd be able to identify the important information that's needed. 2, again, I'd recommend drawing a diagram to make sure that you fully understand the situation. If possible, necessary. 3, and at this point, you are going to develop equations. So you're going to find a constraint equation, and an objective equation. So in related rates, you have one equation that you need to find. For optimization problems, you'll need to find 2 in general. So the constraint equation describes the restriction. What's the restriction? Pretty much the given amount. Right? So if we're in the situation where I described that situation to you, the farmer situation, hey, a farmer has 100 feet of fencing. I specifically gave you the amount of fencing that we have. There's that number 100. I don't have an infinite number, a length of fence. I have 100 feet of fencing specifically, right? So it's a given amount, it's very specific. That's a restriction. I can't use as much fencing as I want. I can't build a fence around the whole world and give him the biggest area to plant his crops. I have a restriction. So I need to come up with an equation that describes that restriction. So obviously, if you want to build a rectangular fence, my equation is going to have to do with the perimeter, and then I'm going to set that equal to 100 using the variables that I use to draw the diagram. The objective describes what you want to maximize or minimize. What you want to maximize or minimize. Right. So in this case, it would be your area equation, right? So farm has 100 feet of fencing, right? So, and I know he wants to build a rectangle. I can just draw a rectangle. Okay, this is X, this is Y. And the constraint would, of course, be 2x plus 2y equals 100. And I know I'd want to maximize area equals X and Y. And this example I actually did in class, so that's why I'm not writing it down or anything, because I've actually went through this in class. But it's a very nice and simple example to show you the concept on, right? So you would come up with these equations. So this equation would be called your constraint equation. This would be called your objective equation. 4. Let me write it in the other way. 4. So once you find those two equations, you would solve for a variable in constraint plug it into the objective. The point get the objective to have one variable. Okay, so you'll notice here my objective has two variables, X and Y. That's an issue. I'd want only the variable X or only the variable Y. I can accomplish that by going to this equation, solving for either X or Y, and then plugging it into the other equation. Right? Because we don't know calculus 3, so we can't actually deal with derivatives when there are more than one variables in a non-implicit case. So 5, you are going to maximize the new objective or minimize. And this comes down to finding the absolute max. However, usually the local min or max will fit this rule. So remember, finding absolute max and mins account for you taking the extremes, plugging in the endpoints. In a lot of situations, this actually won't make any sense. So for example, if we look at the fencing example, the same farmer, then you might say, okay, he has to create a width X and a length Y. What are the endpoints for X and Y? Technically, these endpoints would be 0 or 100. He could apply the minimum, the bare minimum he could put for the width is 0. 0 fencing on the width. The maximum he could put is 100 fencing on the width. However, in this situation, it wouldn't actually make sense to do that, right? Because if there's 0 width, it means there's no rectangular enclosure. It's just a straight fence. Also, if the width is 100, that would mean that the length is 0, which again, there's no rectangle, right? So plugging in the endpoints won't actually make sense in this context. And in a lot of physical contexts, it usually doesn't, at least in calculus 1, right? I mean, in general, the endpoints can be the solution. So oftentimes there's going to be a point in the middle where you want to find the maximum or minimum. You're never going to actually get the maximum or minimum at the endpoints, not usually. And I don't think I would ask you a question where. I don't remember if your homework has a situation where the endpoints was actually the solution. But in practice, I don't think I would give you a question where the endpoints give the solution. So usually it ends up being you want to find a local max or min. Usually also, whenever there's just one answer, you find a critical point, there's only one critical point, that's going to be the guy you want. It's going to end up being the max or min. However, it's best that you test it. You can test with the first derivative test to make sure that it's increasing on the left, decreasing on the right if you want a maximum, as well as you might be in a situation where you get several answers for critical points and you want to know which one do I pick. If you want the maximum, you have to pick the one that's the maximum. If you want the minimum, you pick the one that's the minimum, right? So you maximize or minimize. And then 6, and this is sounds strange, but you'd answer the question. So at the end of the day, something very specific is going to be requested. They might ask something like, what are the dimensions of the fence, right? In which case you would tell them the length and the width. They might say, well, what is the maximum area that he could build? In which case you would tell them the area, right? So depending on what is requested of you, once you get through step 5, you'll have all the information to answer any question. So just make sure that you follow up by actually answering the question that was asked, right? So they'll ask you for something very specific. Make sure you give them that specific thing. And that's basically optimization in a nutshell. And again, if you haven't seen that lecture, maybe it's none of what I said is going to stick, but hopefully in principle, it kind of makes sense to you how it would work. Any questions on optimization? Anything that I said might sound crazy. It's possible that a lot of you haven't even watched this lecture yet. But what I wanted to do in this is just sounds good. All right, thank you. So what I wanted to do today with you guys is just to highlight the important things that you would need to know about these topics. Not really go into any specific examples unless you guys had some in mind, but just to give you an idea. I know some of you would be watching the lectures where some of these things were spoken about, and in hindsight, my summary will make sense here. So I'm thinking of ending here just because I know you guys still have more work to do. You have more lecture material to cover today. So unless there are any parting questions, I will end now. Any other questions that came up while I was going through anything else you want to know? Okay, so Porter's good. So yeah. Last quiz next week. It's on the stuff that I was talking about during this lecture. Thank you for confirming there are no questions. 3 weeks after that is your second test. The second test is not cumulative. It'll cover the things that the syllabus says it covers. Overlaps will just be incidental. So yes, I'm not going to directly test you on derivatives, but you do have to know about derivatives to do all the things that I'm asking you to do anyway, right? So it'll cover the things that I mentioned that are mentioned in the syllabus. 2 weeks after that is your final. At some point, I'll probably also reach out to you guys about just that extra study session where it's not about specifically the math, but just about how you should go about studying, how you want to organize your final weeks to make sure that you end strong. We'll probably talk about that, and I'll reach out to you guys. I will also remember to send at some point today, send out the quiz grades. I apologize for forgetting to do that. So if there are no questions, I will let you guys go, get your study on, do some more homework, do some more practice. If any questions come up, reach out to me, and I'll let you know. Okay, so are we good in terms of questions? Are we okay? Can I leave you guys? You're not totally lost? Okay. All right. Well, take care, guys. Have a good day. Have a good week. Good luck on the quiz next week. Reach out to me if you have any issues.
Thank you.
Okay. All right.
Thank you.
Thank you.
Thank you.
Okay, doke. You're welcome. Thank you for your joining. Thank you for your attention. And that's that's all I have for you today. So I will see you guys in the next one.